workshop number 3 of Celesymposium 2.0, organized by the Aerospace Society of Delhi Public School, RKPUR. The session for today will be taken by Professor Satya Chakravarthy on electric aircrafts, the future of emission-free aviation. Before we begin, there's a basic set of instructions everyone is supposed to follow during the session. Now we'll be showing you the teaser of Celesticon 2020.
Moving on.
Right. Moving on to our sponsors who have helped make this event possible. Next slide, please. Houston Crampton. The University. The University of Arizona. Cascade. Wolfram Language. Gen.xyz. And Interviewee. Now we would like to hand over to Professor Satya Chakravarthy to speak on the topic of electrical aviation. Thank you so much, sir.
Good. Thank you so much. Shall I start sharing screen?
Yes, sir. Sure.
Are you able to see my screen?
Yes, sir.
Good. A little background about myself. Thanks for having me at Delhi Public School. So I'm Professor Satya Chakravarthy from IIT Madras, and I'm co-founder of the E-Plane company, a startup that is trying to make electric car taxis. So I thought this may be a good time for me to actually talk about electric planes in general. I have a few slides here, about maybe 15, 20 slides. I'm going to get to the point of actually showing a couple of equations maybe at the end, just to prime your thoughts, but largely would like to keep this more interactive. And it's okay for people to actually, is it okay for the audience to ask questions, Zonish?
Yes, sir. We will be having a question and answer session at the end.
And they type the questions and then somebody reads it for me, or I can read and answer. Is it right?
Yeah.
Yes, sir.
Okay. So, yeah, so the audience does not get to talk. That's what he's saying. Okay. All right. So let's just move on. Yeah, I just wanted to point out that the idea of actually having electric planes has been around for a fairly long time, even before I was born, which is fairly long back. And but of course, they didn't really take much shape. And as a matter of fact, even today, we don't really have commercially viable electric planes, but they are pretty much very close to launching them, including what we are doing ourselves here at IIT Madras. Just wanted to point out this. It is very similar to electric cars, as a matter of fact. Electric cars actually were running the roads by the turn of the 20th century, which is the last century. And then they were replaced by the IC engine cars a little quite early in that century, and then for about 100 years and continuing even now, it's IC engine cars that have been ruling the roost. But you can clearly see that it's now going to actually go through one full cycle and then come back to electric cars very soon, as it is already happening. Just a second. Yeah. What I want to do in the next few to several slides is to go over a bunch of different electric aircraft that are around in the world that are being developed and so on. May not be commercial, but at least demonstrations and all that stuff. So here is, for example, a more like a glider, but powered by electric propeller, like a single electric propeller, and it has like about 23-meter wingspan at a 42 kilowatt brushless motor and powered by lithium-ion batteries. That's one. The second one is a Archaeopteryx, and this is again a glider type single passenger aircraft, about stall speed of about 30 kilometer per hour, and ability to glide 28 kilometers after being dropped from an altitude of about 1 kilometers. So that's actually as aerodynamic as it can get. NASA actually did this project on what's called as distributed electric propulsion in an experimental project called X-57 Maxwell. And so the distributed electric propulsion here is where you have 12 propellers on each wing, as you can see. So the motors are very small, therefore you can now wire them up with the battery in the middle. And so it has about 18 electric engines, if you will. And then it has a cruise speed of about 320 kilometer per hour, and a range of about 740 kilometers on hybrid power. Hybrid power is where actually you have the engines coupled with the electric motors. The Chinese E-Hang has been one of the early developments at a duration of about 25 minutes, and probably I think it can go up to about 30 kilometers, if I will. It has about a speed of about 100 kilometer per hour. They have implemented and demonstrated this in Dubai, and looking at trying to implement this over there. There's another one which is done by Chip Yates and Bert Rutan, and it actually broke the electric airspeed record of about 250 miles per hour, and it also intends to break the range record. But of course, there are many such competitions that are coming up on electric planes. There is Crystalline. These are like single-seater. Maximum design speed of about 290 kilometer per hour, 30 minutes of autonomous flight. Look at the that duration over which it can fly is like about 25 minutes, 30 minutes, that kind of time. Or alternative of 15 minutes of autonomous aerobatics at speeds of about 250 kilometer per hour. It has a 192 kilowatt equivalent water-cooled DC brushless motor, and it's the smallest four-motor electric plane in the world by far. Zunamero, on the other hand, is actually on the other side. The smallest of those planes actually has about 12 passengers and has a range of about 700 miles, and a fairly quiet aircraft for the size it has. And Zunum has plans of making much larger planes as well. And of course, I think Zunum is having trouble raising funds and proceeding with So a lot of these actually have background histories that are different from what they have claimed in the past and what they currently represent. Volocopter, for example, I think this is a single-seater demonstration that we are seeing there, but I think they have now done a two-seater. Has about a range of a maximum range of about 17 miles, or let's say I think times 1.6 will take you to about 25 kilometers, or no, more than that, but 30 kilometers, and a flight speed of about 43 miles per hour. Maximum flight time is about 27 minutes, and so on, right? So not very much. Pipistrel Alpha Electro is actually a Slovenian airplane maker with a two-seater and a 40 kilowatt motor, 150 kilometer per hour, and an endurance of 1 hour in the air. And Airbus E-Fan, so this is a demonstrator. It's a two-seater, endurance of about 60 minutes, which is 1 hour, and a cruise speed of about 160 kilometer per hour, which basically means that it doesn't go too far if you think about it, right? So it's essentially 160 kilometers is what it can do in 1 hour. The reason why I'm saying 160 kilometers is too small is something that we will understand quite later. Lilium Electric Jet, again, has a 300 kilometer range and a 300 kilometer per hour, and this is a vertical takeoff and landing. So just want to go back and also show Volocopter is a vertical takeoff and landing aircraft. EHang is a vertical takeoff and landing aircraft, but these are essentially multicopters without wings. Lilium and a lot of other things that I've shown is actually fixed wing aircraft, which cannot take off vertically. They need typical runways and airstrips. But if you now look at Lilium, it can take off vertically and tilt its what's called as electric ducted fans forward in order to be able to go forward. So this is hybrid between fixed wing and vertical takeoff. So this is the first one of those that we are seeing here. Aviation Alice is actually one of the large planes with 9-seater, 9 passengers and 2 crew. It has a range of about 1046 kilometers and a cruise speed of about 482 kilometer per hour. So you can actually see how long it will last, right? So the endurance is something that you can calculate. This is actually taken off and shown first flight about a few months back. Yeah. So there are lots of such vehicles. I think there is, we talked about Volocopter, EHang, Lilium, but there is also Joby Aviation, and there is Archer, lots of such aircraft that are being made. Many of them are vertical takeoff and landing or VTOL, right? So the fully electric planes that are conventional, which is horizontal takeoff and landing, or you can have fully electric vertical takeoff and landing. These VTOLs can actually be either multi-copters or fixed wing and VTOL hybrid. And the propulsion also could be hybrid. It doesn't have to be fully electric. It could be a combustion engine that is actually generating power, and that power can be used for, there is generating electric power, and then that electricity can be used for propelling the aircraft, or that's probably like a series hybrid. But you can also have a parallel hybrid. The combustion power directly powers the propellers, but you also have a battery bank that powers the propellers in parallel. So there are multiple ways by which you can do this hybrid propulsion of combustion engines as well as batteries together. Then there is a combination propulsion, which is you can do for the vertical takeoff and landing. You can do electric. For the purpose of cruise, you can do combustion. The power required for vertical takeoff and landing is a lot more when compared to going forward. Because when you go forward, particularly if you have wings, you're overcoming only the wind resistance. The wind resistance is far less when compared to the weight of the aircraft, which you have to balance and overcome when you're taking off and when you land. So you might argue that, wait a minute, it makes sense to actually do combustion for vertical takeoff, but forward can actually be with electric because it doesn't require too much power. But then from a noise perspective, let's say you're actually fast sleeping in the early morning, and your neighbor is wanting a taxi, and then the taxi takes off from your neighbor's terrace, and it makes a lot of noise while taking off, and you actually get woken up and get irritated. So from a noise perspective, it makes sense to actually do electric while takeoff, and then combustion over the cruise. And it also means that combustion will allow you to go much longer distances in cruise, and so on. So there is always some advantage that you can incur from the different combinations. And then, of course, you can have manned or unmanned. Of course, I mean, that's still, I think aerospace is still somewhat sexist. They don't call it human. We should probably do that. So they call it manned or unmanned, and it could be piloted or autonomous. So both combinations exist. That means even if with passengers, you may have an autonomous flight and not necessarily have a piloted flight, and you can have an autonomous unmanned or a piloted unmanned. Piloted unmanned basically means that you're taking cargo with a pilot and so on, right? Yeah. So I'm going to come to a shifting gears here and then start doing some little bit of analysis. And I want you to think along with me in doing this, because it's actually very simple. It's not even, I won't call it mathematics. It's more like arithmetic, right? So it's just multiplication, division kind of thing, right? So let's suppose that we actually form a company called Tesla, right? I don't know how many of you know there is a plane called Cessna, and of course there is a car company called Tesla. So you could form a company called Tesla, which essentially is taking a Tesla battery and putting into a Cessna. Of course, you can also you can have a competing company called Tesla, which is doing the same thing, right? So if one of your friends is forming this company called Tesla, you can form a company called Tesla, which is competing with it. So what does this company do, right? Whether a Tesla or a Tesla, we essentially slap like a Tesla Roadster battery pack on a Cessna 182 Skyline, a four-seater plane, right? So let's just take that and do this. So let's say, for example, you want to maintain the cruise speed at around 269 kilometer per hour, right? And power the same propellers. Don't even change the propeller, nothing, right? And so the power to the propeller actually must be the same, which is about 172 kilowatts. Now, the Tesla battery pack energy capacity, right, is actually about 200 kilowatt hours. That is the pack at the bottom of a Tesla car, a Roadster. And its energy density is about 207 watt hour per kg. All right. That is on a per kg basis, its energy is about 207 watt hour. Now, we want to find out like how far this aircraft would go, the Cessna would go, if you replaced its fuel tanks and engine with a Tesla battery pack, right? This is what we want to do. So range is nothing but the cruise velocity or cruise speed into the time it takes, right? The endurance. And energy is nothing but power times time, right? So from a power and energy calculation, we can find out what is the time available to expend the energy, right, at the rate at which the power is getting consumed. And that would be take a 200 kilowatt hour energy that's available on the battery pack and start spending it at the rate of about 172 kilowatts, which is what the propeller will consume. And you will find that this plane can actually go for about 1.16 hours. So if you now say 1.16 hours is actually the time it takes to be in the air, and its cruise velocity is about 269 kilometer per hour, you can just figure out like the range that you get with the Tesla battery pack is about 312 kilometers, right? Now, the Cessna Skyline, 182 Skyline, with a full fuel tank that it has, you fill it up with fuel, today can actually go up to what 1,722 kilometers. Whereas this is doing something that is far less than that, like let's say about one sixth or whatever it is, right? So that's the problem that we will be facing when you're now trying to move from a conventional plane to an electric plane. So although Elon Musk has actually done a great job trying to come up with this company called Tesla, right? He's extremely quiet about electric planes, right? So, and you know why, right? So his best battery that he can get, like about 207 watt per kg, will not go too far if you now try to put it in a plane, right? This is the basic idea, right? Now, let's actually flip the problem the other way, right? So the battery power of about 200 kilowatt per kilo, sorry, 200 kilowatt hour at an energy density of about 207 watt hour per kg means that it is actually weighing about 966 kilograms. This is actually the battery pack that is there in the Tesla. Now, just to give you a sense, like a typical a four-seater Maruti car, right, a hatchback or whatever it is of the order of about 1 ton in weight. That's about 1,000 kgs. Whereas the battery alone in the Tesla is actually weighing about 966. That is the battery that is there in that car. Okay. Now, whereas if you now compare that with the Cessna 182 Max takeoff weight, it's actually only 1406 kgs, right? That's only slightly more, heavier, about 1.5 times heavier than a typical car because it has its wings and all that stuff, right? And its empty weight is actually 894 kgs, which means without the fuel tank and without the passengers, right? So the fuel weight is actually about 512 kgs, and the engine weight is about 199 kgs. So the total weight of fuel and engine is about 711 kgs. Now, instead of taking my 966 kgs worth of battery, I'm actually allowed to take only 711 kgs worth of engine weight and fuel, right? That means I want to keep my total weight the same. In which case, if you reduce the battery pack to about 711 kg to match the above, then the available energy, because it's coming at about a 207 watt hour per kg, is the what call energy density. Therefore, a 711 kgs of battery will actually mean I won't get 200 kilowatt hour. I'll actually get only about 147 0.18 kilowatt hour. And if I were to actually do the same calculation as in the previous slide, I will get a time of only about 0.86 hour, and therefore the range is only about 230 kilometers. So this slide essentially says I want to maintain the weight of the Cessna exactly the same. The previous slide, we did not bother about it. We didn't really bother about what is the weight of the battery, right? The weight of the battery is actually in excess from the 711 that is allowed. It's actually going all the way to 966. So, but and there is a price to pay for that, right? So we didn't bother about it in the previous slide. But now, if you want to keep in mind that no, I can't allow for my aircraft weight to increase, and I want to keep it at that, I can go only 230 kilometers with a Cessna, and compared to a 1722 kilometers, right? So just keep this in mind, right? This is the fundamental problem with electric aircraft, that the range is extremely limited. So let's actually try to sort of algebraize, if you will. I mean, if I don't know if you've heard of this term, I just cooked that up on the fly, right? So if I want to actually put all of that stuff symbolically, like in algebra, instead of not even this is like what I mean. This is still maths, just putting symbols to it instead of numbers, right? It's still arithmetic. So what we did was to actually say that range is nothing but speed times time, and the time was nothing but the energy density, that is E star, times the mass of the battery, right? This is actually the total energy that's available in the battery divided by the power of the battery, right? So if I were to actually plug that as so the essentially energy divided by power is the time. So I just plug that back and then get this range to be speed or velocity, whatever you want to call it. I mean, it's just unidirectional path. So you don't have to worry about the direction. So vector, scalar, don't worry about that. And so you now say V infinity times the energy divided by power is essentially the range. So now the question then is like, what is the power of the battery? So the power of the battery is whatever is the aircraft's power divided by a certain efficiency. Because all the power that is sucked out of the battery is not going all the way to the aircraft. There will be losses in between, right? So there will be a propeller loss, there will be a shaft loss and gearbox or whatever it is, right? A lot of bunch of things that will actually be making this lossy when compared to what is the battery actually giving away. So you divide it by an efficiency. This efficiency could be like about 0.8, right? That much. So the battery has to give you like about 20% more efficient, power when compared to what the aircraft actually takes. And so what is that aircraft that is actually taking? It's nothing but the thrust provided by the propeller, and the thrust provided by the propeller times its velocity, with which it actually goes forward, is essentially the thrust provided by the propeller is overcoming the velocity at which it is going, and therefore the power incurred is thrust times that velocity. And the thrust is actually equal to the aerodynamic drag. That's the reason why we need the thrust. So there is a drag that comes across along the, against the plane, the wind resistance. And this drag is actually equal to the thrust. That's why the plane can actually go at a constant velocity, V infinity. Therefore, drag times V infinity is actually the power incurred by the aircraft. Right. Now I'm going to write this drag in a slightly different way. I'm going to write this drag as it's in the numerator, you see. Then I'm actually going to push it to the denominator of the denominator, right? So I'm actually going to get it to become like L by D, right? Where L is nothing but lift, and lift is actually what's being generated by the wings, and that's equal to the weight of the aircraft. That's what is the wings supposed to do, right? It's generating lift that's equal to the weight of the aircraft, so that the aircraft stays up in the air at a particular altitude constantly. And the weight of the aircraft is nothing but mass of the aircraft times gravity. So I can write this drag term as a mass of the aircraft times gravity divided by L over D. Now, L over D is actually more like an aerodynamic efficiency. How sleek is my aircraft in generating lift versus how draggy it is, right? So if it is very sleek, it produces a lot more lift and incurs much less drag. So a very good L by D is always nice, right? So this is what is now your power. And the power of the battery then is going back, right? You plug this formula over there, and then you will find that eta total is showing up at the denominator. Now go back and then use this battery power. This is the last slide, right? Battery power, and then you now plug that in there, and you will find that you can actually rearrange things, and then you get this blue box. So the blue box is actually a very nice formula. It says, so the range is actually directly proportional to how dense your energy is in the battery, right? How much energy can you store in the battery for a given mass of the battery? So the battery should not be too heavy, but it should actually be very energetic, right? So that's what E star is all about. Now, eta total is the efficiency. If the efficiency is very high, whatever is the battery, putting out on as its power, it'll be directly getting taken by the aircraft propeller, right? So that has to be as close to 1 as possible. Gravity sucks. It literally sucks you down, right? So if you were in like a lunar or a Martian gravity, it's better, but of course, lunar, you don't have air, but Martian, yes, possibly yes, right? So if you have a lesser gravity, you get a greater range. No marks for guessing that. L by D is actually the aerodynamic efficiency, as I said. So you want to have a very sleek aircraft, and the mass of the battery divided by the mass of the aircraft, right? Well, let's say, for example, the entire aircraft were actually made of battery. That's possible, right? So we look at some very brainy people and then say you have a body full of brains, right? Sort of like that. So you have this entire aircraft made of battery, and then that becomes unity. Then you also get like a very high range. But otherwise, obviously, the aircraft has a lot more stuff when compared to the battery. Which means that this term, M battery divided by M aircraft, is going to be less than unity. How much close to unity it is depends on how light the aircraft is otherwise. And that is a matter of the structures. So typically, when you get into aerospace, you will see that broadly there is aerodynamics, structures, and propulsion, right? And this equation actually gathers all of them, right? And E star is actually the propulsive. E star and the eta total is actually the propulsive part. The L by D is the aerodynamic part. And then the M battery by M aircraft is actually the structural part. Now, if I were to compare this with what happens with regular combustion-based aircraft, the corresponding formula actually is slightly different. It has this natural logarithm 1 divided by 1 minus M fuel divided by M aircraft. Right, slightly complicated. I'm going to show you why this actually happens this way in I think about the next slide. Yeah, I think it's probably the next the second last, right? So if you now look at how a conventional aircraft works, that's a blue line, and that goes by this the natural logarithm stuff, right? That is the blue formula over there. and the red one is actually the electric aircraft. Okay, so now the x-axis here, the horizontal axis is actually either the M battery by M or the MF by M, depending upon whether it is a fuel or battery, right? As your aircraft gets bigger and bigger, and as the fraction of the aircraft is a fuel or battery, then you're going to get this x-axis to go rightwards, or we'll be going rightwards along the x-axis. Now, if you now look at this red curve, that is actually the electric aircraft formula. If you look at the blue curve, it is actually the combustion aircraft formula. And you can see that it actually keeps on diverging more and more, right? And if you now look at the Cessna for which we did the calculation, they aren't too far apart. We're about 6% low. But if you now look at something like a Boeing 747, that's like the jumbo jet, right? You now have a significant drop in the range over the combustion aircraft. Why? And why did we, first of all, have this complicated looking term called natural logarithm 1 divided by 1 minus m fuel by m and all that stuff? It's mainly because as you are flying, you are spending the fuel, the aircraft gets lighter. So a lighter aircraft can go that much farther. And then as it goes farther, it's burning more fuel and it's getting even lighter. So it can actually go still farther. So by virtue of actually using fuel and spending fuel and pushing the fuel out as exhaust gas outside the aircraft getting lighter is actually able to extend its range. Now, if you try to have a battery, then the battery is only exchanging electrons, and it's not even throwing electrons out. It's just exchanging electrons within the aircraft, and electrons actually are hardly of any mass anyway, right? And then they don't even get out of the aircraft. So there is nothing that you're actually losing in terms of weight of the aircraft as you go. That remains constant, right? So therefore, you actually get like a linear a curve. When compared, linear curve is basically a straight line, whereas you get like a curve over there for the conventional aircraft. So going to larger and larger aircraft and making them electric is somewhat disadvantageous over the combustion aircraft, whereas when you now go to smaller aircraft, it's okay to electrify and you're not losing a lot. This is the moral of the story in this picture. So if you were to actually try to do this for all different aircraft, let's say we now say we got a 4-passenger Cessna 182 Skylane, we got a Pilatus PC-12 with a 12-seater aircraft, with a Dornier DO-328, which is a 30-seater aircraft, an Embraer, which is like a E170, which is a 70-seater aircraft, and an Airbus A320 with about 150-seater aircraft. The combustion range, you can see, actually keeps increasing with the number of passengers, right? And that's because the aircraft is larger and larger. You have a larger fuel tank and you can put more fuel and you can go longer for farther. And then you're also expanding the fuel. The aircraft gets lighter. It pushes your range even further and so on. That's as we saw in the previous slide. But you now see the ranges are all in 4 digits, right? And then it starts from something like what 1695 for the 4-seater and goes all the way to about 6650 for the Airbus. Now, the interesting thing is we have not really seen like a Cessna go for about 1700 kilometers in one shot, or a Pilatus travel for about 2200 kilometers in one shot, or even the Airbus actually going for about 6650 kilometers in one shot. Usually, well, you can. The point is essentially it says that you can do long distance, but you normally don't do long distance, right? So in India, for example, you would use an Airbus A320 to go from, let's say, Chennai to Delhi, and that's actually about some 2000 kilometers. That's, you still have another 2/3 worth of range available with a full tank of the engine. So in some senses, combustion aircraft are being overpowered, if you will, with all the fuel. But and look at the electric, all of them actually have only 3 digits, and then those numbers are not very far apart, right? They're depending upon whether I'm replacing a heavier engine versus lesser fuel or vice versa. I get like very different results. They're not even like going in one a monotonic way. This is about 222, 316, 260, 214, 211. the L by Ds may be different, all of that stuff, right? So they're all about 200 to 300 kilometers range. That's it when compared to, all of these. So this is primarily where we are. And if you now were to actually extrapolate this to, let's say, foreseeable future, end of this decade, and take into account how the battery energy densities could improve, right? You can clearly see that the ranges can actually get better and better and better, but still they're not climbing beyond about 600 kilometers, even for the Airbus A320. And for a lot of others, they're all in the 300 to 400 kilometers range by the end of the decade is essentially the outlook with the current lithium ion technology. I think that's all I have. I wanted to actually keep this talk pretty short so that I can try to take questions as much as possible rather than I want to actually talk only for about half an hour and keep the remaining 1 or 1.5 hours, however long it can last. Yeah. So I would be very happy to take more questions rather than give a talk.
Thank you so much, sir, for the session. It was a really informative session. I learned so much and it was quite interesting. We'll just start with the Q&A. We already have some questions popping in, guys. All right.
Right. I think the first question there is, why do we need electric aircraft? Okay.
Mhm.
Right. In fact, in my course that I teach on electric aircraft, the next segment of what I talk about after I have actually introduced up to this point pretty much, right, is about what is called as technology disruption. So I don't know if you guys have actually heard of this term called disruptive technologies or technology disruption, any of those kinds of things, or disruptive innovations, right, and so on, right? What is meant by disruption? So it looks like a very disruptive word by itself, right? It's sort of like suddenly saying that we will. I mean, disruption sounds like a negative thing, like everything is going on smoothly, and then you're suddenly putting a spoke. So this word was actually introduced by this person called Clayton Christensen, who wrote this book called The Innovator's Dilemma, and in which he basically points out what it takes for large companies to fall and new companies to emerge, right? And sort of like almost a sutra for the making of new companies and the fall of older companies. These could be like 100-year-old companies suddenly falling down. Like the best example we can think about is Kodak. So Kodak being or Nokia, right? Many of these companies, they did not change what they were doing. So Kodak was actually doing these chemical-based, film cameras, right? And keep asking more questions, guys. I'll keep answering them, right? Kodak was actually doing these chemical-based film cameras, which actually literally has infinite resolution, right? That means you can take that picture, you can project it on a bigger and bigger and bigger screen, and you will still not see any dithering, right? You will see the faces and stuff as clearly. At that time, in about 30 years back, digital cameras were actually pretty lousy. And people ask exactly this question: why do we need digital cameras, right? And 30 years then from now, I don't even know if you know what is meant by a chemical film camera at all, right? You'll have to see that in the museum today. And another similar example is Nokia's phone, which was not a smartphone, right? And today, nobody uses these kinds of things. So this is exactly what's going to happen. When a new technology starts, it actually is way inferior when compared to current technology. And you have to actually see what it's worth and can you find a new market for it to grow from. And today, with the kind of limitation on the range that I actually showed for the electric aircraft, the new market that we are actually looking at is what's called as urban aerial mobility, which means that if you're in Arkepuram, right, in Delhi, and you want to actually go to Connaught Place, you should actually be taking a plane instead of actually going by road. And because that's a range that actually can be done by electric aircraft, right? That is the new market that these electric aircraft will get into and will grow out of, or grow from, I wouldn't say out of, and start taking on the larger aircraft over time, so that you will progressively actually see in about 10, 15, 20, 30, 40, I don't know, years, all planes will actually become electric, right? That's the journey that we're going. And that's exactly the reason why I'm actually giving this talk to you people, right? Because the way this is actually happening, electric aircraft are actually the future of aircraft itself, right? That's the reason why I'm actually talking about this. Good.
So the next question is that what if electrons were pushed out of the plane? Would it be more fast than the combustible plane?
Unfortunately, no. It's a great idea, because I don't think electrons will do as much harm to the climate as what we are doing right now with carbon dioxide emissions. But electrons actually are next to photons in mass. I mean, they hardly contribute to any mass loss to the plane, right? So the plane's weight is not going to significantly get lighter with pushing electrons out. And electricity works by closing the circuit. That means the electrons will have to actually come back. So there is no way you're going to push the electrons out and then start thinking about there is no open circuit that's possible with electricity. That's another problem, right? It's sort of like a hypothetical question, but take it in its own weightage. What is hypothetical today could actually be possible tomorrow, but the major problem is electrons are too small, too light to become appreciable. Yeah.
Is it possible to use solar energy for aircrafts?
Absolutely. So Solar Impulse 1, Solar Impulse 2, those aircraft that were actually going around the world, right? So it also happened, like it landed in Ahmedabad, and then it took off from there and then landed in Varanasi and then went out of India. No marks for guessing those two places. You know who the Prime Minister is and what he does with these two places, right? So yeah, so there is solar aircraft that is possible. It's just that today solar panels are actually too heavy, very less efficient. So you need like very large wingspans, and you need to have like sufficient real estate in the aircraft for putting solar panels to produce the power that you want and then fly. So there are a couple of examples there, but they're not like commercially viable at the moment.
Like you said, that we can make small electric planes without severe consequences, and we know that electricity still takes fossil fuels to generate. Wouldn't it be possible to go to put solar panels that can withstand the speed and air pressure on both smaller planes and some larger planes?
So I just answered the same question that was actually asked in one line, but let me just a little bit elaborate, because this question is a bit longer. So we need to give some weightage for a longer question with a longer answer. So yeah, so let's imagine that you can actually come up with solar panels that are sort of like foils, right? That's happening now. Like there are these organometallic polymers which can actually work like solar panels, right? So you coat a solar panel material on a flexible sheet and all that stuff. So is it possible for us to actually come up with like some extremely lightweight wings that are just about sheets, and then you coated solar panels on it, right? The answer is, what is their efficiency? The efficiency is like too small. So you need like very large wings for this, and that makes the wings like very wobbly and all that stuff, right? So at the moment it's kind of like not very viable, or not at least commercially viable. But what I wouldn't discount them at all, like particularly the ones that we are making, right? The air taxis that we are making, we are trying to make them extremely compact, so that I don't know how big is your school ground. In fact, we're not even thinking about your school ground. We're thinking about your school's terrace and your apartment's terrace, right? To actually land and take off from. Let's say in about 4 or 5 years, if you want to actually commute to school, you should actually be taking a plane, right? Not even 4 to 5 years. We won't actually do this by 2025, right? So let's say in 2026, you actually are able to actually take a plane from school to home and back. We won't actually land on the rooftop of your apartment and rooftop of your school, right? Not even count on the ground, the playground. So whereas if you are to actually do solar panels, the aircraft will be so large that you need to have like a huge field for this and so on, right? So what I would do is, if you are progressively making bigger and bigger planes with larger wingspans without the constraint of making it very compact, there is sufficient real estate to augment batteries with solar panels. That's what I would say, right? And then solar panels got to get lighter with these polymers and all that stuff. So there is an evolution towards it. Yeah, very long answer once again.
The next question is that, as you mentioned, that combustion aircraft has many advantages, but due to the current condition, the natural resources, which is fuels, are getting less and lesser every year. So the question is that, can we have all the advantages of a combustible aircraft with the new technology?
The answer is much more than the current technology's advantages, right? So we have to actually count our advantages and not the disadvantages. The disadvantage is only range, right? The advantages are, first of all, these aircraft that we're making, the electric aircraft that we're making will be far cheaper than a combustion aircraft. Today, in an aircraft, the engine actually costs about half of the aircraft. The engine is like a super complicated piece of machine, right? So in my view, in the 20th century, people, or even the 19th century, people used to actually get like a lot of fetish about making very complicated technology, right? Whereas that's exactly what we shouldn't do at all. Like, for example, if you look at computer graphics, right, the best computer graphics will be such that it is so natural people don't even know that it's computer graphics, right? And then you have to tell those guys, dudes, actually this computer graphics, it's not real. So real cool technology should not be very complicated, whereas engines are actually very complicated, right? So electric, on the other hand, is like very simple. It's actually as simple as what you would make for like a quiz board, right? So I mean, if I had to actually dumb it down, right? So like a quiz board with like questions on the left side, answers on the right hand side, jumbled up, and you have those board pins, and then you connect them up at the back side, and then you now take like two leads, and then a bulb glows up and all that stuff. The electric aircraft is exactly the same. Right, you have a battery, you have wires, you have motors, and you just hit the switch, and then the motors start running, and then that's what it is. So the simplicity actually allows for the cost to come down significantly, right? And as I said, you can't pack a lot of battery into the aircraft like what you do with cars, right? And that is the reason why you're actually suffering that very low range, because the aircraft has to fly, so you can't actually pack a lot of battery. Right, and battery is the single most expensive item in the aircraft or the car. So current electric cars are more expensive than conventional cars because you're trying to pack a lot of battery to get about the same range. Whereas here, if you now say, okay, I can't match that range anyway, so I'm going to put only that much battery as allowed to maintain the weight of the aircraft. There's a limit on how much battery we can put, and therefore the cost of the aircraft comes down significantly because the battery is not there too much to be expensive. So the asset price of my aircraft is actually very less, the ownership, right? The maintenance is very less, the number of parts is extremely less, the number of moving parts is very less, and the operational cost, right? As fuel prices keep on rising, whereas electricity prices keep on falling, I would want to fall back on electricity. And the other thing about fuel prices is that it's not like they actually keep on rising, they fluctuate a lot, right? From something like about $30 a barrel for the crude to about $120 per barrel of the crude. They just fluctuate a lot, which means that people like airlines and many of these people who are operating this, they'll not be able to foresee or forecast what their next quarter's margins will be. Okay, and that makes it very hard for them to actually run the business. Whereas if I had like a flat curve and particularly very low, cost curve, it is actually much cheaper to run electric aircraft. So what we feel is that electric aircraft will penetrate the market far faster than what you expect, because it will just disrupt aviation. It will just make everybody wanting to fly because it's become so affordable. Right?
Yes, sir. The next question is that, till which year will we get the batteries powerful like fuel, if there's any estimate?
Oh yeah, there is a very, very simple estimate. Never. Right? Fuels are actually super energy dense, right? So the aviation turbine fuel that's actually being used actually has a energy density of about something like 13,000 watt-hour per kg, right? Whereas a battery today actually has something like about 200 watt-hour per kg. The closest that's actually getting there is what we call as lithium air, whose theoretical energy density is about 12,000 watt-hour per kg, right? But we hardly reach the theoretical energy density at all. It's usually about 30 to 40% of the theoretical density is what we achieve. So there is absolutely no visibility to getting anywhere close to the fuel. Yeah. So sorry to disappoint you there, but I think that's okay, not a problem. You don't need necessarily, I mean, you can ask the question, how is the fuel compared to, like, let's say nuclear power? And then nuclear power will be actually a lot more, right? So, you can get disappointed with fuel too, right? But we don't, right? We don't think about like a nuclear aircraft. Well, maybe that's a talk for the next, RK workshop, right? So, but we're not talking about that at all. So electric is okay, not a problem. Yeah.
The next question is that, do you believe that with the advent of more energy dense, smaller and more efficient batteries using different compounds, apart from using them in just aviation, we may also use them for space exploration?
Oh, yes, of course. So today, space exploration has two parts. Okay, one is to first of all get to space, right, from Earth's surface, and then second one is to explore space. So the actual term space exploration is all about getting to space as like the biggest hurdle when compared to actually going further into space to do whatever you want, to go to the moon or Mars or other planets or outside the solar system and all those things. Those are actually far easier when compared to actually getting out of Earth, because Earth sucks, literally. It actually has gravity that sucks, right? So when you now try to beat gravity, batteries are not going to do it no matter what, because that's going to be a very hard sell and we don't allow nuclear rockets at all. That's actually banned by international convention anyway. So I'm not really seeing rockets use better and better batteries, but they actually can assist these batteries. So, for example, we have the other startup that that I'm part of called Nickel, where we're using these battery-powered motors for turning pumps that will draw the propellant and pressurize and push it into the combustion chamber, right? Those batteries right now are lithium-ion, right? But if I were to actually change them to like metal air batteries, I can start using the oxygen on board, right, instead of actually using air, because the air as well, the oxygen is actually what's getting into the battery and reacting. Nitrogen is a diluent. So if I don't have the diluent and I'm using oxygen, I get like much better batteries that can allow me to take more payloads, right? So the rocket gets better, but I can't think of replacing combustion for getting out of Earth. But going deep space, yes, it's possible to do completely with batteries, is my guess. Yeah.
In the coming future, is it possible to increase the range of electric planes with the addition of solar cells on its surface? If yes, how long do you think will it take before it's feasible for complete commercial use?
Yeah, the quick answer is yes. And my guess is it'll take at least about 10 to 15 years. Yeah. The reason for that is very simple. You need, I think it's actually possible in places like India. The reason for that is in India, we have a lot of people, right? Which means that even if you want to do something not so long distance flights, right, there are enough people. So if you look at what we did was we actually did about 50 aircraft in the world ever that have ever been made. And we plotted the number of passengers with the range. And we find that the larger the number of passengers, greater is the range. We also showed that chart, right, with the 4-seater to 150-seater, the range keeps on increasing. That's actually the general trend. Whereas if you now make it electric, all these ranges will actually pretty much be the same. The question then is like, if I were to actually convert a 150-seater Airbus A320 into electric, and right now I'm actually having like, let's say a 200 to 300 kilometer range, but batteries improve, and then I have enough wing surface and all that stuff to put solar panels, and I'm actually able to extend this from, let's say, current 200 to 300 kilometers to something like of the order of about 800 to 1,000 kilometers. Wow, that's great, because I can actually start flying from Chennai to Bangalore, Chennai to Hyderabad, Chennai to Bombay, Chennai to Trivandrum, any of these places, right? The answer is that can happen in about 10 years. It doesn't have to actually wait for too long. Why 10 years? Because somebody has to give me the money. And for me, for people to actually give me money, they need to trust me, right? So for that, I need to actually show at least a 2-seater aircraft flying, right? So that is actually the biggest problem. It's not as if the technology is there, right? So somebody has to trust that this is possible and put in money for seeing this market. Whereas in countries elsewhere, you don't really have cities in such close proximity, except like, let's say, northeast of the United States or somewhere in Europe and all that stuff, right? So and you don't have so many people. So the cost economics works out that the larger the number of seats, which requires you to have larger wings than the solar panels, right? You need to have a longer range. Whereas that economics does not actually hold good for India. Even for short distance, we have like large number of people, right? So India is actually a very good place to actually look for larger electric aircraft with solar panel assists to happen, except that somebody has to actually trust somebody else and then put the money to make this happen.
So the next question is that, can you explain the working of electric propellers in aircrafts and spacecraft electric propulsion?
They are vastly different. Both of them basically work. Let's look at what's common, right? So both of them actually work on what's called the jet propulsion principle. That is, you throw stuff behind you at a greater velocity than what comes in. In the case of rockets, you're not taking anything in, right? So whatever you throw back is what's actually going to push you forward. And definitely it is something that's thrown back at a faster rate than even your forward speed, even though you're not taking in any air or whatever it is, right? So you have to, and the reason why that's important is because in space, you don't even have air to come in, right? But you want to actually throw stuff out. This could be combustion products, or it could be electric ions and all of that stuff, or some gas propellant that you have used in a tank that's pushed into an engine and heated up and then pushed out faster. So fundamentally, you're actually putting something out and you're moving forward. This is Newton's third law stuff. But that said, a propeller is actually taking air in, and it's now working on it and pushing by increasing the momentum and then pushing it a bit faster. An electric rocket, on the other hand, will have a gas that is stored in a tank and then takes it from there and heats it up and pushes through a nozzle and moves forward. So this is the main difference between the two.
Yes, sir. A couple of months ago, the world's first flying car was tested. So do you see a greater significance of it in the commercial sector?
Yeah. I mean, it's not just a couple of months ago, and that's not the first one, right? So there have been quite a few electric planes that have been made. There's a slight difference between what's called a flying car and what we call as an electric plane. People are actually fancying about flying cars being cars that can actually drive on the road and then suddenly spread their wings and then start flying as well, right? And then come back on the road and then fold their wings and then behave like a car, right? That's somewhat complicated with all those moving parts like folding wings and all that stuff. We don't know whether they will get certification to as a foolproof or a failure proof. What if like the wings got actually stuck, while you're in flight, right? Or what if the wings actually started folding down, right, while you are in flight, right? You'll actually fall like a brick. So anytime you actually have these kinds of moving parts like hinges and all that stuff, the regulatory authorities get very jittery. They say, sorry, it's all too complicated, right? It's all good for nice like one-time thing, and if you have money, you can blow it up and make like one prototype and show something, or maybe it's stuff for science fiction and all that stuff, but not for like regular passengers, unless you actually prove its reliability, that no matter what, it'll always fold up when you want and fold down when you want and all that stuff. So that is the flying car. Okay, but there are a lot of other electric aircraft. I showed like a lot of pictures of electric aircraft. I didn't show quite a few other pictures of what we call as electric VTOLs, right? Vertical takeoff planes, which actually move forward like a plane with wings, but takes off vertically like a helicopter or a drone. There are many of them that are happening, and we are just about around the corner. In about 1 or 2 years, we would start seeing them commercially in action and taking people, charging for it about the same as Uber prices, or a little bit more, and so on. Yeah, these are just waiting to happen in India.
Sir, would it be possible to use wind energy for these aircrafts?
I doubt it. Many times people have this notion that you can actually take the wind that's coming in and then generate the energy and then put it back into the aircraft and then use it to push. That is what we call in thermodynamics as a perpetual motion machine. right? That means that there is no energy consumption. You're not having to pay anything, for this. That's actually a fallacy, because the amount of energy that you can harvest from the wind that's coming at you as you're flying is actually less than the energy that it will take for you to be able to fly, right? And the very fact that you're actually trying to harness the energy by putting like a windmill is going to increase the drag of the aircraft a lot more, and that will require you to actually spend much more energy in order to overcome that, right? So that essentially is the second law of thermodynamics. So my answer is, I think it's no. Unless you're coming up with other ways, right? So for example, let's say you came up with some, I mean, I'm just guessing these things. If you came up with some nice piezoelectric crystals that can line up the side of the aircraft, and the wind essentially shears this, and then it produces electricity and all that. Okay, it's a very different way than just having a conventional windmill. So my thinking is, keep thinking these things, right? Don't give up, right? And don't listen to an old man like me, right? Right? Any of these new ideas, don't even ask me whether it's possible, right? So in fact, you should be able to challenge me rather than ask me whether it's possible. I might say no because I have like a lot of baggage, right, to unlearn. You can come up with new ideas completely.
The next question is that can smaller aircrafts like the volocopters replace cars or buses?
Not exactly replace, in my opinion, but can replace a bit. Let's say, for example, that's what I keep telling, right? So let's say there are about 12,000 taxis in Chennai, the Uber Ola variety, right? We expect that about 2,000 air taxis, right, of the kind of your volocopters and all that stuff, can actually totally replace those 12,000, because each trip in air takes only about 10 minutes or 12, no, right? So I don't know how long it takes for you to actually go from school to home, right? Let's say, for example, it takes a 30 to 40 minutes to get from one place to the other in Delhi or wherever, right? Navi Mumbai or wherever it is, right? What we're talking about is to get that actually happen in about 5 to 10 minutes, which means that an electric aircraft can do about 3 to 4 trips in an hour. And even if it actually does about 7 to 8 trips before it needs to actually charge, right? So about 2 hours of operation, half an hour of charging, 2 hours of operation, half an hour of charging, and so on, right? Or maybe 3 hours of operation and 1 hour of charging. I don't know, right? You can do something like about 40 to 50 trips in about a 20-hour period. I'm not even thinking 24 hours, right? It's possible that between midnight to 4 a.m. there aren't too many trips. So in a 20-hour period, we can actually think about anywhere like about 40 to 50 trips. Whereas a typical taxi in a very crowded traffic city is not more than about 5 to 10 trips. So there is like about a 8 to 10x difference in the number of trips that are made by an aircraft when compared to a road taxi. So a 12,000 taxis can be replaced by about 2,000 aircraft. And for 2,000 aircraft to populate the city skies may take maybe about 10 years, is my quick guess. It could be sooner, I don't know. But I don't expect a complete replacement of all these road taxis by air taxis. That's my guess. So maybe up to about 50%. Yeah.
Okay, now I think we should start wrapping up. It's already quite some time. Thank you so much, sir, for being a part of our event. It was truly an amazing session.
Thanks
I'm
a
sure
lot.
everyone learned a lot from all the examples you provided, as well as the case study that you presented. It gave us, quite unique insights about the challenges that need to be faced to bring commercial electric aircrafts to reality. I don't think there are any more questions. Thanks again, sir. And attendees can start leaving.
Okay.